Have you ever looked up at the night sky, filled with its countless stars, and wondered what it's all really made of? We know about atoms, and the even smaller particles inside them, like electrons and quarks, but what if that's not the end of the story? What if, when we zoom in further and further, past the limits of our most powerful instruments, we find something completely unexpected? What if the fundamental building blocks of everything in the universe, from the largest star to the smallest speck of dust, are not particles at all, but something else entirely? A cosmic secret, waiting to be revealed. This is where one of the most exciting ideas in science comes in: string theory. Imagine a guitar string. When you pluck it, it vibrates. Depending on how it vibrates, it produces different musical notes. String theory suggests that the universe works in a similar way. At the very heart of every particle, there isn't a tiny point. Instead, there's a minuscule, one-dimensional loop of energy. It's a tiny, vibrating string. These strings are unimaginably small, far smaller than anything we can currently detect. They are the true foundation of reality, hidden deep within the fabric of space-time itself, constantly in motion. Think about all the different particles we know: an electron, a photon of light, a quark. According to this beautiful idea, these aren't different things at all. They are all just different notes being played on these fundamental strings. A string vibrating in one specific pattern appears to us as an electron. A different vibration, a different pattern of movement, and that same string manifests as a photon. Another vibration, and it becomes a quark. The universe, then, is not a collection of tiny billiard balls. It's a grand cosmic symphony, with all of matter and energy arising from the music of these vibrating strings. So, everything you see around you, the chair you're sitting on, the air you're breathing, the light from your screen, is all part of this symphony. The rich diversity of our universe, with all its complex structures and phenomena, could emerge from this simple, elegant principle. The laws of chemistry and biology, the very existence of stars and life, could all be traced back to the harmonies and melodies played by these tiny, energetic strings. It's a profound shift in perspective, suggesting a universe that is not just a collection of matter, but a dynamic, musical, and interconnected whole, vibrating with untold potential. For centuries, physicists have been on a quest for a single powerful idea that can explain everything. We have one theory, Einstein's general relativity, that masterfully describes the grand scale of the cosmos. It explains gravity, the force that holds planets in orbit and galaxies together. Then we have another set of rules called the Standard Model of Particle Physics. This model is brilliant at describing the other three fundamental forces of nature: electromagnetism, and the strong and weak nuclear forces that govern the world of tiny particles. The problem is, these two theories don't speak the same language. They work perfectly in their own domains, but when you try to use them together, for example, to describe what happens inside a black hole, or at the moment of the Big Bang, the math breaks down. It creates nonsensical answers. Physics has been searching for a theory of everything, a single framework that can unite gravity with the other forces, a theory that could write the entire rulebook of the cosmos in one elegant equation. This is one of the biggest challenges in all of science, and it's a puzzle that has stumped the greatest minds for decades. String theory enters the stage as a powerful contender for this ultimate prize. It doesn't just suggest a new form for matter, it has the potential to be the bridge that connects these two great pillars of modern physics. Remarkably, one of the notes that a string can play, one of its specific vibrational patterns, perfectly matches the properties of a particle we've theorized about but never detected: the graviton. This hypothetical particle is believed to be the carrier of the gravitational force. The fact that gravity naturally emerges from the mathematics of string theory is not a small thing. This is why physicists get so excited. String theory doesn't just accommodate gravity, it requires it. The same framework that describes an electron also describes the force that keeps our feet on the ground. It suggests that all the forces of nature, which seem so different to us in our everyday lives, are actually just different manifestations of the same underlying reality. They are different tunes played by the same cosmic strings. If string theory is correct, it would be the successful completion of a search started by Einstein himself, providing a single unified description of all matter and all forces in the universe. The journey of string theory is a story of scientific creativity and perseverance, built over decades by many brilliant minds. it wasn't the discovery of a single person, but a growing symphony of ideas. In the late 1960s, scientists like Gabriele Veneziano were studying the strong nuclear force and stumbled upon a mathematical formula that, unexpectedly, described vibrating strings. Initially, it was just a curiosity, a mathematical tool that seemed to work for a specific problem. It wasn't yet seen as a fundamental theory of the universe, but the seed of a revolutionary idea had been planted. The idea truly began to blossom in the 1980s, thanks to the work of physicists like Michael Green and John Schwartz. They showed that string theory wasn't just a quirky mathematical model, but could be a consistent, viable theory for describing all fundamental particles and forces. This period, often called the first superstring revolution, ignited a firestorm of excitement in the physics community. They demonstrated that the theory could be free of the mathematical inconsistencies that plagued other attempts to unify physics, giving it a solid foundation to build upon. Later in the 1990s, another giant leap was taken by scientists like Edward Witten. At the time, there were 5 different versions of string theory, which was a bit confusing. Which one was correct? Witten proposed a stunning solution during what is known as the second superstring revolution. He suggested that these 5 different theories were not competing ideas at all. Instead, they were all just different perspectives of a single, deeper, and more mysterious 11-dimensional theory, which he called M theory. The M is mysterious, standing for magic, mystery, or membrane, depending on who you ask. This idea was a game changer. It suggested that strings weren't the only fundamental objects. There could also be higher dimensional objects called branes, short for membranes. Our entire universe could in fact exist on one of these branes, floating in a higher dimensional space. The work of these scientists and many others transformed string theory from a fringe idea into one of the most active and promising areas of theoretical physics. It's a testament to how bold thinking and collaborative effort can push the boundaries of human knowledge into entirely new realms. So, why does this strange, unproven idea continue to capture the imagination of so many people, both scientists and the public? It's because string theory does more than just try to explain the world we know. It hints at a universe far stranger and more wonderful than we ever conceived. It challenges our most basic intuitions about reality itself. One of its most mind-bending predictions is that our universe doesn't just have the 3 dimensions of space, length, width, height, and one of time that we experience. For the math to work, string theory requires the existence of extra, hidden spatial dimensions. These extra dimensions aren't something you can step into. The theory suggests they are curled up, or compactified, to a size so infinitesimally small that we can't perceive them. Imagine a garden hose. From far away, it looks like a one-dimensional line, but for an ant walking on its surface, it clearly has a second dimension. The circular path around the hose. In the same way, every point in our space could be a tiny, multi-dimensional shape, a space within a space, where these extra dimensions are curled up, hidden from our view. This opens up astonishing possibilities. Could there be other universes? Some interpretations of string theory connected to the idea of branes suggest that our universe might be just one of many, like a sheet of paper in a vast library of other papers. These parallel universes could be floating in a higher dimensional space, possibly just millimeters away from us, yet completely inaccessible. This isn't just science fiction, it's a possibility that emerges from the equations that physicists are working with today. It changes our place in the cosmos from being the center of everything to being just one possibility among countless others. String theory is still a work in progress. It makes predictions that are incredibly difficult, if not impossible, to test with our current technology. But its power lies in its ability to ask the biggest questions and provide tantalizing potential answers. It pushes us to think beyond what we can see. What other secrets is the universe hiding in plain sight? What other dimensions, forces, or realities might exist just beyond our reach? The quest to understand the cosmos is the greatest adventure of the human mind. If you want to continue this journey and explore more mind-bending science, be sure to follow our channel for the next cosmic revelation.